Hi everyone, so we are going to solve this particular problem without the concept of feedback topology now. First thing is we need to find the gain. What is gain? I naught by Is. So our target is to find I naught by Is. Is your I naught by Is. Here I wrote one thing, that is there, make proper assumption. Make proper assumption and find find I naught by Is and Rx and Ry. So what is that assumption? Let's just assume, forget about assumption and anything. Your target is to find I naught by Is. So what you will do? First you will see that whatever I do, this will be shorted. So to proceed with the question, at least I need the potential of this point. To proceed with this question, I need the potential of this point, because then I would know the current and then I can do something in the particular question. Because if I know the current here, then I can know the voltage here, then something will happen. So at least I need to know the potential of this point. Say yes or no, right? Or if not the potential of this point, at least you need the current in this MOS. Your target should be at least I need the current in this MOS. In MOS amplifier, what is the current? If I know the current in this MOS amplifier, I would know this voltage. If I know this voltage, then I could write down the I out value as well. So this is my target. Now, if you see at the output, this is your output voltage, right? So output voltage have two paths now, this path and this path. Now, can you say your I out, this current, let's just assume this current, I'm calling this current as Ix. Can you say your Ix is Rm upon Rm plus Rf into I out? Can you say like that? No, you cannot say, right? Because this node is not grounded. This node is grounded, this node is not grounded. If this was grounded, then you could have said it, right? The current here would have been this much. So what is the other way that you assume voltage V here? Then what do you know that here there will be GMV current. Now this GMV current is there, that means this voltage will be GM RD into V. Then the current here would be GM1 GM2 RD into V, and that is equals to I out. Now you apply different voltage and current equation and then you can get to your final answer. But that is a very hectic process. That's why I told you make proper assumption. So what is the assumption that I am going to make? Now listen to me very carefully. Okay, let's just remove it off. So it would be a very tough problem if I don't make any assumption. So what is the assumption I'm going to make? What I know that here there is current feedback topology. Current feedback topology is there. For current feedback topology, what is the input impedance? Rin is very low, right? Input impedance is very low. What is your input impedance here? This is your V in by Is, right? V in by Is is very low. Is is a finite quantity that user will apply. So if I take V in to be very low, is there any issue? I can take V in to be very low. I can take V in to be nearly equals to 0. Say yes or no. Why I am doing so? Because I know for a current feedback topology, the input voltage will be very low because the impedance is very low. If the impedance is very low, the input voltage will be very low. So for a current feedback topology, for current feedback topology, I can take V in to be very low. So this is the assumption I am going to make. In this problem, if I hadn't make any assumption, if I don't make any assumption, this problem will be very time consuming, there will be a lot of equation. But smartly I got to know that this is a current feedback topology, and in the current feedback topology, I know that my input impedance is very low. So I can take an assumption that V in is nearly equals to 0. I can take V in nearly equals to 0. So this node will be nearly equals to 0. If this node is nearly equals to 0, so what you can write? What this current would be? This current would be Rm upon Rm plus Rf into RL, right? So this current would be So I am calling this current as Ix. So Ix current would be Rm upon Rm plus Rf into I out. So this Is current is also there, this Ix current is also there. So this current would be Is plus Ix. Is plus Ix. So what will be this voltage drop? Let's just remove it. Let's just remove it off. This voltage drop will be in this direction. So this voltage drop will be Is plus Ix into Rd. Right? So what will be the current in the downward direction? That would be Gm2 Rd into current in the downward direction, Gm2 Rd minus Gm2 Rd Is plus Ix, and that will be equals to I out. Right? So what you saw here, minus Gm2 Rd Is plus Ix. What is Ix? Ix is Rm upon Rm plus Rf I out. Rm upon this current is equals to I out only. Right? So minus Gm2 Rd Is I out into 1 plus Gm2 Rd Rm upon Rm plus Rf. What will be your I out by If? I out by Is, sorry. I out by Is. That would be minus Gm2 Rd divided by 1 plus Gm2 Rd into Rm upon Rm plus Rf. Say yes or no. Well and good, right? So this is the closed loop gain without using the concept of feedback topology, but here we use the concept of feedback topology only for one assumption, that is V in would be nearly equals to 0. V in would be nearly equals to 0. So this is the assumption we have made, and based on that assumption we got this final answer. Well and good. Let's find the next thing, that is input impedance. What will be your input impedance? So let's find out input impedance. So I will copy the circuit once again. I will remove the other things and then I will find the input impedance. Yeah, so I need to find the value of Rx. So it would be Vs by Is. So here I am taking Vs by Is. So my Rs would be Vs by Is. One thing I know, that Vs is very small. Vs is very small, but still I need to get the value, so I cannot directly ignore it, right? So if this potential is Vs, then what will be the current? This Vb will be gone, this Vdd will be gone, this Vdd will also be gone. This is gone, this is gone, this is shorted. This was your M1, this was your M2. So what will be the current in the upward direction? That current would be Gm1 Vs. What will be this node voltage? That would be Gm1 Rd into Vs. What will be the current in the downward direction? What will be the current in the downward direction now? Right? That would be minus Gm1 Gm2 Rd into Vs. So this is the current. Right? Your target is to find Is by Vs. So from Vs node I know this current. I just want this current now. I just want this current, because then I could apply the nodal analysis at Vs. Right? So I want this current. What is the current coming here? This current is minus Gm1 Gm2 Rd into Vs. Now again I will make the assumption that Vs is very small. So now you can directly divide the current. So what this current would be? Let's call this current as Ia. So what would be Ia? The Ia would be Gm1 Gm2 Rd Vs into Rm by Rm plus Rf. Say yes or no, because I am making an assumption. What is the assumption? Assumption is Vs is very small. Since this is a current feedback topology, I can make this assumption that Vs is very small. So what did I do? I took Vs here, the current I wrote, then I wrote the potential, then I wrote the current. If this is the current, that means this current will be divided into Rf and Rm. So Rf will take Rm into Rf, Rm upon Rm plus Rf into the current value. So this will be your Ia. So now at the Vs you can apply nodal. What is the nodal analysis that you can apply? That is your Is plus Ia is equals to Gm1 Vs. Is plus Ia. What is Ia? Ia is minus Gm1 Gm2 Rd into Rm upon Rm plus Rf into Vs is equals to Gm1 Vs, right? So Is is equals to Gm1 plus Gm1 Gm2 Rd, Gm1 Gm2 Rd into Rm upon Rm plus Rf, and then in common there is Vs, right? So what will be your Vs by Is? That would be 1 by Gm1, because Gm1 would be coming common. So 1 by Gm1 divided by 1 plus Gm2 R2. So that would be a complex expression. So I should write in better manner. Vs by Is would be 1 by Gm1 divided by 1 plus Gm2 Rd Rm upon Rm plus Rf. That's it. This is your Rx voltage. Sorry, I have not voltage, Rx resistance. 1 by Gm1 divided by 1 plus Gm2 Rd Rm upon Rm plus Rf. Right? Okay. Now I need to find Ry. So let's find Ry. It will also be a hectic task, I guess. Let's find Ry. With the concept of feedback, it will be very easy, but without the concept of feedback, we need to apply a lot of equations. So that's why I'm teaching you this concept of feedback, because in the examination, you can recheck your answer with this concept, right? You need to find Ry now. So what you will do? This will be gone. This is already shorted. This is already shorted. This is already shorted. So you need to find Ry. So if you need to find Ry, what you are going to do? You will apply a Vy potential here and get Iy out of it, right? And here this is completely gone. So my target is to find Vy by Iy. So yeah, I tried solving this particular Vy by Ry in rough only. So these are the expressions that have been written. So this is becoming very complex. If you try to find out Vy by Iy, it is becoming very complex. I am getting very complex expression. So without the concept of feedback, finding Vy by Ry is very difficult here. Your equations will be very complex and it will create a lot of problem. So I'm going to write here Ry equals to Vy by Iy. It will end up in complex expression. But with the concept of feedback topology, we can reduce it. So now we are going to apply the concept of feedback topology with the concept of feedback topology. So with the concept of feedback topology. So with the concept of feedback topology, we are going to solve all those problems. Because here at Ry, हमने हार मान ली, ठीक है? We have given up here because that was very complex. Actually, I am solving all those problems with you only. First I am trying to think what should happen, and then here I am teaching you. So when I solved it, I show you the expressions as well. Then it was very complex expression. So better we solve it with the concept of feedback topology. So with the concept of feedback topology, now we are going to solve. So first thing, we need to make the open loop. So how will you make the open loop? The current is coming. Now this will be also very interesting. You will see very interesting result here. First tell me what kind of feedback is that? Negative feedback, right? It was a negative feedback. So this was the feedback loop. This was the feedback loop. You need to break it up. You need to break it, right? So here the feedback current was coming. This was the feedback current. Now if I take this direction of feedback, what will be fed in the input side? In the input side, what will be fed? Is plus if. Say yes or no. So basically this will be your block diagram now. That from here is coming and you are feeding if, but that is positive. Then what will happen? Even if it is a negative feedback system, still your result would be a upon 1 minus a beta, or r in, because r in you need high or low, you need r in to be low. So r in upon 1 minus a beta and r naught into 1 minus a beta. This it will result into, although it is a negative feedback system, but it is being added here. And now if the gain is positive, then what will be the final answer? A upon 1 minus a beta. Why is it so? Because it is being added. That's why it is being added. So better, if I need to subtract it, I will take the opposite direction of the feedback. I will take the opposite direction. So this direction I am going to take. So what will be fed now? Is minus if. So when we studied those block diagram of different topologies, these block diagrams I am talking about. Which block diagrams? These block diagrams. So that was the reason I took the direction to be inside and outside. So I told you, no, you can take any direction, but to make it in the negative feedback, to make the formula correct, I was taking those kind of directions. So similarly I am doing it here. Okay, so now I need to make it a open loop. So I will break the loop from here. If I am breaking the loop from here, what will happen? Where is that gone? Okay, I will again have to draw it. This was your feedback. You want feedback current to be zero. You want feedback current to be zero. If you want it to be zero, that means this node will be open circuited, and you want your feedback current to sustain here, so this node will be grounded. Say yes or no. This node will be grounded because you want this to sustain. You are breaking it from here. You want zero current. If you want zero current, that means this will be open circuited. You want it to sustain, that means it needs to be grounded so that IF current flows. If you keep it open circuited, IF current cannot flow. So you want it to sustain. So this is your open loop now. So what is your open loop? Your open loop is, let VDD will be gone. This is your RD, and then you have a MOS. This will be grounded. This is your IS. This node will be open circuited. This is M1, and this node is connected here. This is grounded. This is V out. This is RL. This is RM. Right, and this node is V out. This is your RF, and you want it to sustain, so this will be grounded. Say yes or no. And this was your I out. What is your target? Your target is to find I out by IS. I out by IS. So IS current is flowing. IS current is flowing in this direction. IS current is flowing in this direction. So it will give you a drop of ISRD. It gives a drop of ISRD. This is your M2. So what will be the current downward? The current downward would be minus GM2 IS into RD. Minus GM2 IS into RD, and that is equals to I out. So I out is equals to minus GM2 IS into RD. Right? So what is your open loop gain? I out by IS open loop, that would be minus GM2 RD. This is your open loop gain. Let's talk about open loop input impedance. So I will copy this circuit. If I need to calculate open loop input impedance, then I just need to see from this side. From here, I will apply Vs here and get Is out of it. So what will be my open loop input impedance? Similarly, simply it is 1 by GM1. From here you see 1 by GM1 only. Now people will say, sir, why are you not considering lambda here? If lambda is not equal to 0, that means R naught is finite. Pagal ho jaogi. You will get mad. If R naught is finite, you will get mad. It will be a very complex analysis. 1 by GM parallel with whatever will come. A lot of things will be coming. So it will be a very tougher analysis, right? So we are ignoring R naught here. What about your R naught open loop? R naught open loop. From here you need to see R naught open loop. So what you will do? Let's remove this. Let's remove this. Let's remove this. Let's remove this as well. Why so? Because if you are taking R naught open loop, this will be gone. This will be completely gone. So here this node is gone. So this current will be gone. This node will be simply shorted. This node will simply be shorted. If this node is shorted, so what do you see? You see, if this node is shorted, this VSG is gone. So what do you see? You will see that RL plus RM parallel with RF. And generally feedback resistance is large. Generally feedback resistance is put larger. So it would be RL plus RM. Okay, but let's just take this is your final answer. So RL plus RM parallel with RF. So this is your R in open loop, R out open loop. What is the feedback factor? What is the feedback factor? So here I can write the feedback factor. So what was your I out? Sorry, what was your IF? IF would have been RM upon minus RM upon, because there will be negative sign. So minus RM upon RM plus RF into I out. Say yes or no. This would have been your feedback factor. So what would be your feedback factor? Your feedback factor beta I. Your feedback factor beta I is minus RM upon RM plus RF. This is your feedback factor, right? So this is your feedback factor beta. This was your open loop gain. So now you can find all the things. First thing is closed loop gain. Closed loop gain would be A upon 1 plus A beta. What is your A? A is minus GMRD now. Okay, minus GMRD. The gain is negative upon. So what is happening here is that simply you took IF to be in negative direction, right? This is your IF that is being negative. This is positive and negative, and this gain is negative, and this feedback factor is also negative this time. Look, this is negative and this is also negative, and this is certainly negative. In previous cases, what was happening? This was positive and this was also positive. Now both are negative, so still it is a negative feedback system only. Why is it so? Let's check that out. So I will make the loop diagram, because people will be confused now that this is my IS. IF direction I took to be opposite, like IF should be IS minus IF. So IF is being subtracted. So basically this is the IF that we are taking. Now this is the forward gain. Forward gain was negative. So this is negative, right? Then you had some I out. Then you had the backward then you had this feedback factor. This is also negative. feedback factor, you can see this is also negative. Now let's prove if it is a positive feedback or negative feedback. So let's see. If this increases, what will happen to this one? This will decrease, right? If this increases, this will decrease. Why so? Because this is negative, it is being multiplied with the negative value. If this is decreasing, then what will happen to this? This is already negative. If this is decreasing, then it will increase, right? If this is increasing and it is being multiplied with the negative, that means it will decrease. So it is a negative feedback. Both were negative, both blocks were negative. If this was increasing, this was decreasing. If this is decreasing, that means this is increasing. And if this is increasing, this is being decreased. So in the exam, they can frame some block diagram and they can ask you what kind of feedback is that. Then you see there is a negative sign, so it is negative feedback. No, negative sign does not ensure this is a negative feedback. You need to check if I increase my output, what happens to my output again. So if I increase my output, this will increase, this will decrease. If this decreases, this will increase. If this increases, this will decrease. So that's why it is a negative feedback. So that's why it is negative feedback. So this is how you need to check. So all these things we study in control systems, but control system, analog electronics, network analysis, and signal system, all those four subjects are interrelated. So one day my target is in 2025 I will teach all those subjects together. Okay, so I'm thinking about it. I'm writing the materials as well. So I will teach all those four combined. These four subjects combined. Like you will not be able to understand which subject is going on, whether it is control system or signal system or network or analog. So all these will be combined. I'm thinking about it. Let's see how it goes. Okay, so closed loop gain would be minus gm1, here it was minus gm2 rd upon, so a upon 1 plus a beta. What is our answer? A upon 1 plus a beta. Since this is a negative feedback system, so this is our answer. So a is negative, beta is also negative, so that doesn't matter. I just need to put the value a upon 1 plus a beta. So a is minus gm2 rd, minus gm2 rd is there, minus sign is there, but I am not going to put it because here also there is minus sign, so that will be cancelled. Rm upon Rm plus Rf. So this is the closed loop gain we are getting. It is the same as the previous one that we got. That was also minus gm2 rd upon 1 plus gm2 rd Rm upon Rm plus Rf. Rm upon Rm plus Rf. What is the assumption here? There is an assumption here. When we were finding this value, there was an assumption. What was the assumption? We took, what did we do? We took this node to be grounded. Why so? Why we are taking this node to be grounded? Because we know that Vs will be very low. So that assumption I have already written. So I am taking Vs to be very low. That's why the feedback current is Rm upon Rm plus Rf into I out, and negative sign is certainly there. Right? Okay, well and good. Next I can write closed loop. I forget about closed loop. Just you need to write closed loop impedance, that is 1 by gm1. You need impedance to be low. You need the impedance, you need, for a current amplifier, you need input impedance to be low. So 1 by gm1 divided by this factor 1 plus gm2 rd to Rm upon Rm plus Rf. This is your Rx. And what about Ry? You want your output impedance to be high. So what will be your Ry? Ry will be RL plus Rm parallel with Rf now it will come into multiply only 1 plus gm2. So better I should keep it this way. One plus gm2 rd into Rm upon Rm plus Rf. So I told you this expression will be very complex, and see, this is your Ry, which is very complex. But we finally got it by the concept of feedback topology. We studied about current feedback topology, which was very simple only. So in current feedback topology, we could write the input output impedance very easily because we know input impedance will be low and output impedance will be very high. Then we saw this example. Here we could get to know that this is a current feedback topology. How did we see it? In the input we see there is simply current mixing, and even if you put output equals to 0, still there will be some current coming. So if there is still some current, that means your feedback element is not depending on the output voltage. That means there is no voltage sampling. That means there has to be current sampling. If there is current sampling, so it is current feedback topology. Then we determine these values without the concept of feedback topology, but there we made an assumption that was that your Vin would be very low. Your Vin would be very low. Since this is a current feedback topology, that means your Rin will be very low. So you can take your Vs or Vin to be very low. So then your Ix would be Rm upon Rm plus Rf into I out. And then you could write down the current, then you could write down this current, and then you could find the final I out current. This was the expression. Then you could find the expression of Rx as well, that is Vs by Is. So from there as well you could find the expression. This was also very simple. And then you could find the expression of Ry. No, you could not find the expression of Ry because we given up here because that was very complex expression we were getting. Then we solved it with the concept of feedback topology. First we saw open loop. What will be the open loop diagram? So for open loop diagram, for one node will be open circuited, other node will be shorted, because I don't want any input current to be coming there, and the other node should be shorted. Why so? Because I want my feedback current to sustain. Then in open loop we found the open loop gain, that was very simple, minus gm2rd. We also find the feedback factor. In feedback factor, when we are finding the feedback factor, you are not going to make the open loop diagram. It will be closed loop diagram only. So what will be the feedback factor? That would be Rm upon Rm plus Rf minus sign, because I am taking If to be going outward, so that into the most Is minus If current is going. So into the gain, Is minus If current is going. So this is the block diagram. Is minus If current is going, but here the gain is also negative and feedback factor is also negative. So eventually it is becoming negative feedback only. This is becoming negative feedback only. So R in open loop you have, R not open loop you have, closed loop gain you have, Rx value you have, and Ry value also you have. Well and good. Let's okay. This is being shadowed now. यहाँ पे मेरी शक्ल आ रही है ना? You can see my face, right? But what I have written here, that is closed loop output impedance. So we are going to write the types of feedback topology. We will write the forward gain, we will write the feedback factor, we will write the closed loop gain, we will write the closed loop input impedance, and we will write the closed loop output impedance. So tell me, for voltage amplifier, for voltage feedback topology, what was the forward gain that I was showing with AV? And for voltage current, output is voltage and input is current, that I was showing with AR. And for current voltage, so that means output is current and input is voltage, that will be trans conductance amplifier. So AG I can show, and this will be AI. Well and good, no issue. What will be the feedback factor here? It will be beta V. In case of this one, it will be okay. I was showing it with RM. I was showing this with RM and this with GM. Remember, output voltage, input current RM, and this with GM. So what was the feedback factor here? It was beta I. What was the feedback factor here? It was GM. And what was the feedback factor here? It was RM. What was the closed loop gain? Here the closed loop gain was AV upon 1 plus AV beta V. What was the closed loop gain here? RM upon 1 plus GM RM. What was the closed loop gain here? GM upon 1 plus RM GM. RM GM. And what was the closed loop gain here? AI upon 1 plus AI beta I. What about the closed loop input impedance? So for a voltage amplifier, what will happen? Input impedance will increase or decrease? It will be increased. For a voltage amplifier, input impedance will be increased. So Rin, that is the open loop impedance. So closed loop impedance would be Rin into AV beta V. What about voltage current? What about trans resistance amplifier? So in trans resistance amplifier, output is voltage, input is current. Input is current. That means you want your Rin to be as low as possible. You want your Rin to be as low as possible. What about current voltage? So input is voltage. Input is voltage. That means you want your Rin to be as high as possible so that more and more voltage is coming. So Rin into, why I am writing AV beta V? It would be GMRM, because here loop gain is GMRM. It would be Rin into 1 plus GMRM. And what about this? Input is current. So you would want your Rin to be as low as possible. So Rin upon 1 plus GMRM. नहीं यार, GMRM क्यों भाई? Rin upon 1 plus AI beta I. Because feedback factor is, loop gain is AI beta I, right? What about output impedance? For a voltage amplifier, you would want your output impedance to be very low so that more and more voltage goes towards the load. So R1 upon 1 plus AI beta I. What about voltage current? Voltage current. What is the output? Output is the voltage. If output is the voltage, that means you want your output resistance to be as low as possible so that more and more voltage is going towards the load. R0 upon 1 plus GMRM. What about this current voltage? So output is current. If output is current. So you want your load resistance to be as high as possible so that more current is going in the load. You want your output resistance to be as high as possible, so it doesn't eat up any current and more current goes in the load. What about current? So output is current. So you certainly need your R out to be as high as possible so that more and more current goes in the load. So you want it to be as high as possible. So that's it. So for gate point of view, this table is very, very important. Very, very important. They can ask you, in case of voltage current feedback topology, what will be your output impedance? So you will be able to think voltage current, output impedance. Output is voltage. Output is voltage. That means you need R0 to be very low. So R0 upon 1 plus GMR. This is how you will be able to think about it. Well and good. Let's see very, very simple point. Sometimes you get confused in this one. Some people may have a doubt. So you can get confused sometimes. So what that doubt can be, I will address that. So I have always said that from here to here there is 0 degree phase shift, right? You need to see the arrow. If I go from source, if I go from gate to source, that means there will be 0 degree phase shift. If I am going from gate to drain, there will be 180 degree phase shift. Now I cannot say that, sir, if I am going from drain to gate, what will be my phase shift? 180 degree. Wrong. Why is it so? What I mean to say that I am saying I am coming from here to here and then my phase shift will be 180 degree. This is completely wrong. Why so? Because at drain side you can never apply the input. At drain side you can never apply the input. Here there can never be input. At drain you can never apply the input. We have studied common source amplifier. Input was at gate. When we studied common drain amplifier, input was at gate. When we studied common source, common drain, when we studied common gate amplifier, input was at source. When we studied common gate amplifier, input was at source. And we studied common drain amplifier, input was at gate. You never saw input at drain. Why is it so? At drain you can never apply input. Never apply input. You can तो कर तो कुछ भी सकते हैं. You never apply input. Generally you never apply input at drain. Why so? Because if you apply input here, this will not be depending on this MOS. This will not be depending on GM. If I apply input here, what will be my current? GM V in. If I apply input here, my current would be GM VGS, whatever it is. So my current is depending on VGS, gate and source voltage. My current doesn't depend on drain voltage. When we do the small signal analysis, my current doesn't depend on drain voltage. It only depends on gate to source voltage. That is why I never apply voltage at the drain. So you will never see voltage being applied at the drain because your current doesn't depend on drain voltage. Your small signal current does not depend on The small signal current doesn't depend on drain voltage. That's why you are never going to apply your small signal at drain, right? So you cannot say that sir, I'm going from drain to source, so I will have a 180 degree phase shift. No, no, no. You are going from source to drain, then you are having 180 degree phase shift. And if you are going from here to here, if you are going from source to drain, so you will have 0 degree phase shift, right? So this was one thing. Now other doubt one can have, what is that? That is that sir, what I will do, I will come from here to here. What will be the phase shift? 0 degree. Then I will go from here to here. What will be the phase shift? 0 degree. So that means if I am going from here to here, there should be 0 degree phase shift. What do I mean to say is that someone will say, sir, if this node increases, then what will happen? This node will increase. And if this node is increasing, so this node will increase. So collectively you can say that, sir, if this node is increasing, then this node is increasing. If this node increases, the drain node is increasing. Did you understand what is the doubt? What the doubt you can have? That sir, if my gate voltage is increasing, then my source voltage will increase. If my source voltage is increasing, that means my drain voltage will increase. So now I can say that if my source voltage is increasing, then my drain voltage is increasing. But I told you one thing, if your source voltage increase, sorry, if your gate voltage increases, that means your drain voltage decreases. This is what I have taught you. But here there is a opposite result. So what is the issue here? Why is it so? Look, input will be applied at only one terminal. If your input is applied here, so the only conclusion you can make is that if you go from here to here, it will increase. If you go from here to here, it will decrease. That's it. You cannot make the conclusion that you go from here to here, it will increase, and you go from here to here, it will increase. No. Input is applied at one terminal. So only you can make assumption from here to here only. Now there can be some other input that can be applied here. So now you will make assumption from here to here. If other input is there, then you can make assumption from here to here if other input is there. So that is the way. So only two assumption you have. You can go from here to here and you can go from here to here. Wherever the input is, only at that node you can make the assumption. It's not that, sir, I will go from here to here and then I will go from here to here. No, you cannot do that, right? Input will be at only one place. So when we solve these kind of feedback topology examples, some people get confused. Many times I have seen people getting confused in that. So I hope this is being cleared now, right? What is the issue here? I hope this is being cleared. So feedback topology as an analog designer, it is very, very important. Feedback topology is very, very important. Once you go into the industry, first thing they will tell you that go to Ali Hazmeri's lecture and study feedback topologies. Study the feedback amplifier completely. So this is the first thing as an analog designer you need to do. This is not important for your interviews, but once you crack the interview, once you get into the industry, the first thing you are asked to complete is the feedback amplifiers by Ali Hazmeri sir. So it is very, very important topology, right? So this is the thing that I explained. Sometimes people can have the doubt that, sir, from drain to source, if I am coming, there is 180 degree phase shift, or from drain to source, if I am coming, there is 0 degree phase shift, and if I am going from drain to gate, there is 180 degree phase shift. No, at drain there will not be any input. Well and good. So let's solve these questions. Very easy question they are. So you have to determine the type of feedback and the feedback factor. Determine the type of feedback and the feedback factor, right? So what kind of feedback is there? First you need to tell positive feedback or negative feedback. These you can tell on your own, but let's determine the topology now. Okay, so let's determine the topology. So where is the feedback in this one? Where is the feedback in this circuit? This is the feedback which is being subtracted with the input. This is the feedback VF. This is the feedback. So output current is coming. So current is being sampled. Current is being sampled. Current sampled. And now this current is this current is making a feedback voltage, and that is being mixed with the input. So current sampling and voltage mixing. So this is current voltage feedback topology. This is current voltage feedback topology. Well and good. Understood? Very easy. Also, how you can determine it? How you can determine this thing? You can determine this thing by the concept that I told you. Let's see the mixing. What is the input current? This is the input current, IS. Is it being mixed? No, this is not being mixed. This is completely going as it is. So there is no current mixing. That means there has to be voltage mixing. So there is voltage mixing. What about the voltage sampling? What about voltage sampling? So for sampling, you need to see voltage. So if I short circuit this output voltage, what will happen? Still there will be some I out current, because even if this is shorted, there is some finite VGS and there will be some current. So even if you put your V0 to short circuit, still there will be some feedback. So certainly there is going to be some feedback. So no issue about that. So this is certainly your current sampling and voltage mixing. So voltage sampling is not there. If voltage sampling is not there, that means certainly it is a current sampling. So current sampled and voltage mixing. So it is current voltage feedback topology. And what is the feedback factor? What will be the feedback factor? So what is your VF? VF is I naught RS, right? So what is your feedback factor? Feedback factor is VF by I naught, that is equals to RS. So better I should write as RM. This is your feedback factor, RM. So feedback factor here is RS. Nice, right? So feedback factor is RS. Let's solve this particular problem. So let's see the mixing first. This is your input current. The current has two paths. The current has two paths, this way and this way. So certainly there is current mixing. No doubt about that. Current mixing. Let's see the sampling. So for sampling, you put V0 equals to ground. If you put V0 equals to ground, what will happen? Will there be any feedback? If you put V0 equals to ground, will there be any feedback? No, there will not be any feedback. Look, this I in will be going here. This I in will be getting mixed, right? But from output there is nothing coming. If you put V0 equals to ground, if you put V0 equals to ground, and let's just say this is your I0. So no feedback factor will be coming, because if V0 is grounded, this I0 will be flowing here. That's it, right? So if V0 is not there, there is no feedback. If V0 is not there, there is no feedback. Think about it again. If you put your V0 equals to 0, is there any feedback factor coming in? No, there is no feedback factor coming in. In the RF, only the input current part will be there. This input current part will be there, because in the RF, what will happen? IN will have two paths, MOS and RF. So it will be divided accordingly with MOS and RF, because from here to here it sees 1 by GM resistance. So it will be divided. RF will have 1 by GM upon 1 by GM plus RF current. 1 by GM upon 1 by GM plus RF into IN current RF will have. But from output, nothing will be coming. So if V0 is gone, that means there is no feedback factor is coming. So certainly there has to be voltage sampling. So there is voltage sampling. So there is voltage sampling. So this is voltage current feedback topology. Now let's determine the feedback factor. So this is very interesting. So what kind of feedback topology we saw here? That is, a feedback topology is voltage current. So voltage will be sampled, it will generate some feedback current and it will be mixed with the input. So the input that is going into the MOS will be IN minus IF, right? The voltage will generate some feedback current and the current that is going into the MOS will be IN minus IF. So there is current mixing and from output voltage it is coming. So you need to determine this IF. How will you determine? Can I write V0 by RF is equals to IF? V0 by RF equals to IF? No, because there is this node which is not grounded. But What kind of feedback topology is that? Voltage current. For voltage current feedback topology, your input impedance should be as low as possible, because what is your input? Input is current. For current input, you want your Rin to be as low as possible. So you can take this node as grounded. If this is the feedback topology, that means your Rin with feedback should be low. And if this is low, I can take Vin to be 0. So Vin can be grounded. So what you can conclude from here? That your V0 by Rf is equals to, your V0 by Rf is equals to minus If. Minus If. Right? So V0 by Rf is equals to minus If. What will be your feedback factor? That would be If by V0. That would have been minus 1 by Rf. If by V0 would have been minus 1 by Rf. So this was the solution of first one. This is the solution of second one. Here the feedback factor was Rs. Here the feedback factor was minus 1 by Rf. Why is it minus 1 by Rf? Because since this is output is voltage, input is current. Output is voltage, input is current. So this is trans resistance amplifier. So the feedback factor would have been trans conductance only. So feedback factor has to be conductance. So it is minus 1 by Rf. Well and good. Because the direction If we are taking in this direction, right? So this is the feedback factor. Let's see the third circuit. For the third circuit, let's see the mixing first. So this is your Vin. So here there would have been In. Now In also has two paths, this and this. Now here people will have one doubt, sir, In will flow from here only. Here there will be 0 ampere current, so In will be flowing from here. So how you can say there is current mixing? What people will say that, sir, there is this In current that can flow from feedback path and from the MOS as well. But in the MOS there will be 0 ampere current. In the MOS there will be 0 ampere current, so the complete current will be flowing here. So what kind of mixing is that? Your In current is not being mixed, it is coming as it is. Yeah, it is coming as it is. So what is happening in the block diagram? In the block diagram, the scene is this. Your In is coming, this is plus, this is minus. Your feedback factor, your If is equals to In only. Here there is 0 ampere current. That's it. This is what is happening here. But current is certainly being mixed. From output there is some current is coming. So current is certainly being mixed, bro. Right? Current is certainly being mixed. So there is current mixing. There are two paths. It doesn't matter that the input current is 0. Input current is 0. That's fine. But there are two paths. And if you see the voltage, this is the Vin voltage, no? So this Vin voltage is directly going towards the amplifier. So there is certainly no voltage mixing. There is certainly no voltage. Voltage is not mixed. Voltage is directly going. Here voltage was mixed. Voltage was not directly going. Voltage was Vs minus Vf. Here the voltage is directly going. V in. Direct voltage is there. So certainly there is no voltage mixing. There is no voltage mixing. There is current mixing. So you can write current mixing. Current mixing. And what about the sampling? Is there voltage sampling or current sampling? If you put this node to ground, what will happen? This is your I node, right? From V node there is an I node. I node is not even shown. Wherever the I node is, it cannot generate any feedback factor. It cannot generate any feedback element. If your V node is grounded, there will not be any feedback element, because what will happen? If V node is grounded, this complete In is coming here and this In will also be grounded. So what kind of feedback is there? What is the output? What you are getting from the output? You are getting from output nothing. You are getting nothing from the output. Right? If V node is grounded, you are not getting anything from the output. So certainly there is voltage sampling. Right? Although here I naught is not even shown, this is a gate problem only. They did not even show I naught. So they are directly saying that it is voltage sampling only, because they are not even showing I naught. Also you can see that if I put V naught equals to ground, there is nothing that would come into the feedback. So the next I am calling is voltage sampling. Now it will be more clear when we find the feedback factor. How it will be more clear? So what kind of feedback is that? What kind of feedback topology is that? Voltage current. voltage current. Again what will happen? Voltage current. For voltage current, what happens? Rin is low. If Rin is low, what I can take? Vin to be low. This will be low. So here I can assume this node as grounded. So what is the feedback current? Feedback current I will take in this direction. What is the feedback current? Feedback current would be V0 by Rf, but negative sign. So Vf equals to beta V0. So you need to find If by V0. So If by V0 would be minus 1 by Rf. If by V0 would be minus 1 by Rf. Right? And that is your feedback factor. Feedback factor is minus 1 by Rf. I know this is being a bit confusing for you, but once you have the practice, you will be able to determine the feedback topologies very easily. No worries about that. It is not also that much important, but here we are understanding as much as we can, right? I have told you a shortcut method as well, that is voltage mixing or not. If I put V0 equals to 0, is there any feedback current? Is there any feedback current? No, there is no feedback current. If I put V0 equals to 0, there is no feedback current. So I need to put V0 to be finite. If V0 is finite, that means there is certainly voltage sampling. So voltage sampling and current mixing. So voltage current is the feedback topology. If they are asked to find the feedback factor, so what you will do? For feedback factor, what did I get to know is that I need to find the feedback current. So for feedback current, the thing I can see is that what if V0 by Rf is my feedback factor? What if my V0 by Rf is my feedback element? What if V0 by Rf is equals to If? But that is not possible. That is only possible when Vin is grounded. And then I got to know that this is voltage current feedback topology. Voltage current feedback topology has a very low input impedance. If it is having very low input impedance, that means Vin has to be very low. If Vin is very low, that means I can take Vin to be grounded. So my feedback factor would be minus 1 by Rf. And this is what I am getting here. Well and good. So this is my feedback factor. Everything is crystal clear now, right? You need to revise it once again, then only it will be more clear to you. Let's move on to our questions now. Few more questions we have. You have to determine the sign of A and B for negative feedback. This is the question. You have to determine the sign of A and B. A can be positive as well, A can be negative as well. For negative feedback, that this op-amp is working in negative feedback. Generally, when you study op-amp, what people say that this is an op-amp. If the negative sign is there, if this negative sign is there in the feedback, it is negative feedback, and if positive sign is there in the feedback, it is positive feedback. But this is not the case. I will show you now. Let's start. So let's just assume if we increase this node voltage, we can start from any node voltage. I am starting from here. Generally, we start from the output of the op-amp. What is the output of the op-amp? This is the output of the op-amp. So we are starting from here. So if this increases, what will happen? This will also increase. This is V bias. There is no use of it. I can keep it grounded. There is no use of this MOS. This is just to confuse you. If this node increases, what will happen? This node is increasing. Now you want your output to decrease. You want your output to decrease. So tell me, what should be B? If B is positive, if positive node increases, then output will increase. So B has to be negative. Say yes or no. So B is negative and A is positive. If B is negative, then only your output will decrease. This node increases, this node is increasing. If this node is increasing, and if B is negative, then only your output node will decrease. So A is negative and B is negative and A is positive. Say yes or no. What is the other way? The other way is, if you want negative feedback, you need 180-degree phase shift. If you want negative feedback, you need 180-degree phase shift. How is it so? Let me show you. This is A, this is plus, this is minus. Forget about the input. So if you start from here, this is V0. Let's just assume beta has 0-degree angle. So from here to here, you are starting from here, that you increase this node. So from here to here, there is 0-degree phase shift, right? Now you are going from here to here. There will be 180-degree phase shift, because if this node increases, this node will also increase. But if this node is increasing, this node will decrease. Why there is 180 degree phase shift? Because there is a negative sign. So from here to here there is 180 degree phase shift, and from here to here how much phase shift is there? 0 degree phase shift. Why so? Because if this node decreases, this node will also decrease. So in the complete loop you are getting how much phase shift you are getting? 180 degree phase shift you are getting. And in positive feedback system you get 0 degree or 360 degree phase shift. So in negative feedback, what are the phase shift you can have? 180 degree you can have, 360 you cannot have, because 0 degree is equals to 360 degree. So 360 you cannot have. So 360 plus 180, 540 degree, and so on. So basically it should be 2n plus 1, 180 degree. Say yes or no. And for positive feedback, there can be 0 degree phase shift, there can be 360 degree phase shift, and so on. So it has to be 360 degree and 0, 360, 720 and 1080. These kind of phase shift can be there. This is very clear, right? It is absolutely clear. Or if they both were negative sign, then what would have happened? From here to here there would be 180 degree phase shift, then again 180 degree phase shift, then again 180 degree phase shift. If gain and feedback path both were negative, then what would have happened? From here to here 180, from here to here again 180 and again 180. So 180 plus 180 plus 180, 360 plus 180, 360 is equals to 0 only, so 0 plus 180 is equals to 180 only. So that's why if there is negative sign as well, then also it is a negative feedback system only. So I hope the concept of feedback is more clear now, right? Even if you have studied control systems, just one concept that I have made your concept very clear, right? Well and good. So in negative feedback we always have 180 degree phase shift, and in positive feedback we have 0 degree, 360 degree or so on phase shifts. So this question we have answered. Now we will answer this one. You have to tell the sign of A1 and B1. There can be two possible answer. I am before going into the final answer, I am telling you there can be two possible answer of A1 B1, A2 B2, and then one more answer can be possible. So let's start from here. If this node increases, then this node will increase. If this node is increasing, then this node will increase. Now finally what do you want? From here to here how much phase shift you have? 0 degree, right? You started from here, and you are going here and here. Till here you are having 0 degree phase shift. Finally what do you want? You want total 180 degree phase shift from this. Because this is increasing, then finally you want this to decrease. So you want total 180 degree phase shift from these two op amp. Say yes or no. So if I put, if A1 is negative and B1 is positive, then if A1 is negative and B1 is positive, then from here to here there will be 0 degree phase shift, right? Because B1 node is increasing, this node is increasing, so this node will also increase. So to get 180 degree phase shift, you have to make A2 to be negative and B2 to be positive. Then your A2 should be negative and B2 should be positive. Say yes or no. Did you understand this? If this node increases, this node will increase. If this node increases, since B1 is positive, this node will increase. Now if A2 is negative, then certainly this node will decrease. Because negative node is increasing, that means output will decrease. So this is the first case. This is the first possible answer. What is the second possible answer? If your A1 was positive and B1 was negative, if your A1 was positive and B1 was negative, then if this is increasing, then certainly this would have decreased. B1 is negative, so it is giving me 180 degree phase shift. If this is increasing, this would decrease. Now if this node is decreasing, I want finally to decrease only. So I have to put A2 to be positive, because if A2 is positive, it will not give me any phase shift. A2 is positive, so it will be not giving me any phase shift. So A2 will be positive and B2 will be negative, because if positive node is decreasing, your output will decrease only. So did you understand this point or not? You started from here to here, you have 0 degree phase shift. can show it in a better manner in this way, that from here to here I need 180-degree phase shift, but you started from here and you went till this point. Till this point you had 0-degree phase shift only. There is 0-degree phase shift. Now A1, B1 and A2, B2 can decide. If B1 is negative, so only you are getting 180-degree phase shift. So again you don't need 180-degree phase shift. So A2 should be positive and B2 should be negative. If B1 is negative. And if B1 is positive, that means you are not getting 180-degree phase shift. From the next op-amp you need 180-degree phase shift. So A2 should be negative, A2 should be negative and B2 should be positive, because if A2 is negative, it will give you 180-degree phase shift. Well and good, understood. Very easy question and very conceptual as well, right? Let's move to our next question. This is our circuit C. So let's again start. If this node increases, then what will happen to this node? This is a common source amplifier. From gate to drain you are going, this node will decrease. And if this node is decreasing, you want your final node to decrease only. So what should be B? B should be positive and A should be negative. So even if the feedback is connected to positive part, still it is working in negative feedback. Why is it so? Still it is working in negative feedback. Why is it so? Because here I am getting 180-degree phase shift. From here to here I am already getting 180-degree phase shift. No one can deny it. If this node increases, this node will decrease. So what I will do? From here to here I will get 0-degree phase shift. So if I need 0-degree phase shift, that means I will put B to be positive and A to be negative. Say yes or no. So if this node is increasing, this node is going down. If this node is going down, eventually I want it to go down only. So I would put B to be positive, right? Now what about this? What about this circuit? You can start from anywhere. Let's start from here. This VB and VDD all are there to confuse you, nothing else. So if this node increases, this is a common source amplifier, then this node will decrease. If this node decreases, then what will happen? This node will increase, right? If this node decreases, this is a common source amplifier, so this node will decrease. So if this node is decreasing, that means this node will increase. Now finally, what do you want? You want it to decrease only. So you would put your B to be negative and A to be positive. Because what is happening? You started from here to here. Started from here to here. From here to here, you had 180-degree phase shift. Again from here to here, you had 180-degree phase shift. So 180 plus 180, that is 360. 180 plus 180 is 360. And 360 is equals to 0 only. So from basically from this node to this node, you are having 0-degree phase shift. From this node to this node, because from here to here there is 180-degree phase shift, and from here to here there is 180-degree phase shift. So 180 plus 180, 360. So from here to here there is 0-degree phase shift. Say yes or no. So here you are having 0-degree phase shift collectively. So collectively till here you are having 0-degree phase shift. So if you are going from here to here, how much phase shift do you need? You need 180-degree phase shift. So if you need 180-degree phase shift, you will put your B to be negative and your A should be positive. So I hope the complete concept is crystal clear to you. We have studied feedback topology, we have studied feedback amplifier, we have seen the type of, how do we determine the type of feedback, it is in positive feedback or it is in negative feedback. In op-amp as well, we will deal a lot of questions like that. So I hope the concepts are being clear to you now. You are much more confident in analog electronics. I know this feedback topology topic is a bit complex. This is not that straightforward. थोड़ा सा tough topic है ये, मानते हैं, लेकिन काफी अच्छे से पढ़ा दिया गया है. अगर रिवाइज करोगे तो you will be able to understand this topic very very precisely. There will be some doubts, I know. In feedback topology, you will have some doubts. Even I will have some doubt. I can admit this thing, that in feedback topology, everyone will have the doubt, because this is not that straightforward topic. So we can discuss the doubts for sure. We will discuss good things. We will get to the good final results. Okay, so if you found this video helpful, I guess this will be the last portion of the marathon as well. So if you found this marathon helpful as well, so please do share it with everyone. And okay then, thank you, and please share our channel so that it reaches to maximum people.